Myself, Priya, Assistant Director from National Skill Training Institute, and today's session will be on digital electronics, which is there for the electronic mechanics students. It is there in the ITI syllabus and as well as it is there in the CITS syllabus also. And digital electronics is a very important topic and it is very interesting also. So we'll start with the I have planned like in sessions I have planned. So this is the first session that will start from the scratch. It will start from the basics of what is digital. From that basics we are going to start the class. So any query is there from your side, you can post it in the chat window. I'll reply to your query and you can also give me a hand raise. Yes. I'll share my screen. Yes, can you see the screen? Okay, we will start the class. Someone has given the hand raise. Okay, we will start the class. The first session of the digital electronics is logic gates. So from that, I'll start my class. So we are going to discuss in today's class like what is a digital circuit and where we can see this circuit, why digital is important and why very big subject is given for the digital electronics. What is the use of digital and what is analog? What is the difference between analog and digital? So that is what we are going to see here. The crowd may be the mix-up crowd. Still, we will move from the basics itself. Yeah. So what is digital electronics? So digital electronics is a circuit which will operate completely on the digital signals. So which is digital signal? What is like before going into the digital, what is analog and what is digital? Like you can give me the answers in the chat window. What is analog and what is digital? Any idea? Analog and digital? My voice is not clear. My voice is not clear. Am I clear? You can hear me? Okay. So it's like we have two signals in common. Generally, we talk about when it is coming to the electronic side, we talk about analog signal and as well as a digital signal. So here, the complete digital electronics, you forget about all the analog signals and you concentrate only on the digital signals. So what is digital signals? So here comes the representation of digital signal. So the digital signal is completely like there is nothing in the world of digital. It's only full of ones and zeros. Apart from that, there is nothing in the world of digital. So where are these digital circuits used? Where you can see this digital circuit? So these digital circuits you can see everywhere, right from our processor, which is present in our mobile phone, or else in computer, or else like everywhere. Any electronic signal, you can also find a part of digital circuits present. So this circuit is very much useful for doing all the digital calculations. We need digital circuits. We have to depend on the digital circuits. So it is everywhere. We cannot just tell like it's present here or present there. So it's like the digital circuits are present everywhere. So whatever gadgets you use in your day-to-day life, everywhere you can find this digital circuits. A small portion of digital will be present there. So in olden days, we used to say like the computer can only understand ones and zeros like that. No? Yeah, again, it is made up of digital circuits. That's why they call that as it can only understand ones and zeros. So why digital? Why cannot analog? Where comes the digital signals? How am I generating the digital signal? So before moving into this slide exactly, what is digital? How I can generate digital? Anything which is generated by nature or which is available by nature are all analog signals. There is no digital signal generated by nature. All the signals which is available in nature, all are analog signals. For example, the change in temperature or the change in light intensity or the change in sound, the change in humidity, pressure, all those are analog signals. There is nothing like digital signals. So I see today in the morning the temperature is 20 degree and slowly it started to increase and about 12 o'clock it came to like 30 degree like that. So it is changing with respect to time. So every time morning 6 o'clock the temperature was like 20 degree, and again by afternoon noon it went to around 30 degrees. So it's keep on changing with respect to time. When the time is changing for every hour, every minute, every second, the signal, analog signal, which is also keep on changing. We are not generating, no signal is generated by nature is a digital signal. Then why we talk about digital signal and why this much portion is given for us in the digital part is uh, see, if you want to store your data, for example, your memory card can save around 10,000 songs, or else you can save around 10 movies, 10 HD movies. So these are very fantasy to listen. No? Yes, even in olden days, we used to have tape recorders, and where we will get only around 10 to 12 songs we can able to save in that tape recorders. So those saved the signals. It's not those signals or with the help of those tape recorders will be called as like magnetic tapes. So they work on the principle of that magnetic. They'll put something on the tape and then we will replay those things. But the memory capacity of those things is very, very small. We used to have this much big size of tape at the time. But now if you take in a very small size, I can put around 10,000 songs. 10 GB of movies I can place it on this. So even I can keep it in my pocket. So this much very small size. Even we can't able to imagine how we used to store the old VCR cassettes and all. To see one movie, we had around this much big size of cassettes. But now the 4 5 movies we can save in a very small pen drive. So if you want to save something, if you want to analyze something, then you have to go for the digital signals. Yes. So do you all save songs? Do you all download images, videos? Do we all do that? No. So we all are using the digital thing. Whenever we are saving something to our pen drive or saving something in our phone, yeah, what we do, we are saving it in the form of digital. So once digital comes into our mind, yes, it is again ones and zeros. So whenever you think about digital, you should think about it is ones and zeros. Okay. So what is given in this actually, if you want to save the data, we need a digital. If you want to calculate something using your signals, see, I want to store a song, then I want to change my signal into digital. Okay. I want to do a calculation on temperature. what is the temperature, what is the temperature of April 14th, 10 years back? What could be the temperature? If I want to do that analysis, yeah, I want digital. Then compatible with digital displays. Easily I can see the digital displays. Compatible with computer technologies. I can process something on this. System can be programmed because all the signals are like ones and zeros. So I can easily program my signals. And digital IC families makes everything easier. Here, See here, again, all your digitals are available in the form of ICs. We already know what is a IC. It is a integrated circuit. Everything, whatever we want, we will dump it into that IC. So that is integrated circuit. Whatever operation we want to do, just pick one IC, put all your operations inside that. So that will behave like if I want to record a song, my uh, all the circuits for a recorder, I'll put inside one this much small IC. So that is the IC here. So why we use digital circuits? See, um, if you save the data in your CD drive, then to hear the song back, if you saved the data song in your pen drive or memory card, to hear the song back, this CD or pen drive or memory card will save it in the forms of ones and zeros. So what I need, I want to convert the digital to analog signal, and again I need an amplifier to amplify, and then I can hear the analog sound waves. But to save that, I want to change it back to ones and zeros. So whenever you download a signal, it will saved in ones and zeros. So that's why we need all digital circuits. So things around us, which and all is analog and which and all is digital. Yeah. So we have a analog clock here. The clock daily, what we see is an analog clock, and then a meter to measure a voltage, changing level of voltage. Again, a push type of a control, variable control here. And here, what I have is a digital display I have for the clock. Instead of analog clock, what is shown here is a digital clock. Similarly, some of the digital method of examples are also shown here. See, this is the example of a analog signal. All time it is changing with respect to what? It is changing with respect to the time. But here the digital signals are all time zeros and ones. So only thing we have to remember in digital is uh, it will have only two things. It is 0 or 1. So what are logic gates? So logic gate will know only two things, as we already know. It is 1 or 0, on or off, true or false. So anyway you can call, but it know only two things. So in a quiz program, if you can give me two answers, yes or no. So only those two are allowed in the digital circuits. So we will start with the logic gate. So digital, we know that it can accept only two things, that is only one or else zero. And where digital circuits are used almost in all our gadgets, all the electronic things. We have a part of digital circuits, and whenever it comes for storing some data or analyzing the data, surely you have to depend upon the digital circuits. So coming to the very basic block of digital circuit is our logic gates. So logic gates are the basic element that make up a digital system. Very, very basic. If I want to study ABCD, I'll start from A. So like that, if I want to know the digital system, you have to surely start from gates. So logic gates or switches that turn on and off depending on what you are doing, depending on what the user is doing. Based on that, the logic gate will give on or off. See, this is my logic gate. This is my gate. This is my gate, and my gate can able to do something that is called as a function. And what function it can able to do? It can able to do a function called as logical function. Yes, it is a logic gate. It's a logic gate. It can able to do something, can able to do some function. And what function it can able to do? It can able to do some logical functions. Yes, I'll give some inputs, I'll get some outputs. The input we call it as binary inputs and output we call it as binary output. So binary input in the sense logic gate will know only two things, and what are that? It will know only on or off or true or false or else 1 or 0. Apart from these things, apart from 0 or 1, if I tell 2, it won't understand. If I tell 5, no, it won't understand. So only I have to tell 0 or 1. I have to teach the logic gate to react only for 0 or 1, true or false or anything else, anything from the anything from this above list, no, it will not understand. It will understand only what? 0 or 1, true or false or else on or off switch, on switch or off switch. We have only the best example to remember the gate is this things is we have only two things in switch, two condition in switch, on or off condition. So you can think about those things. So what and all the binary inputs will be? Binary input will be 0 or it will be 1. So similarly, we will get the binary output, and that will also be a 0 or else 1. So what a gate will do? A gate can able to do a logic function. See, this logic gates we are dividing. We have gates like basic gates, and then universal gates, and then special gates. We have gates in these categories: basic gates, universal gates, and then special gates. So we have in basic we have three NOT gate, AND gate, and then OR gate. In special gate we have NAND, NOR, and then XOR and XNOR. Yes. So these are the total basic elements of a digital circuits. See, for logic gates, we have to remember four different things always while studying the logic gates. So that is the first thing is we will be doing the symbol and then logic diagram, then truth table, and then switching circuit. Symbol is how the gate will look like, how I can remember the gate. So if you are, you can see so many signs in the roads, na, for U-turn, for zebra crossing, all those signs we call here as the symbols. So how I can represent a gate, that is called as signal. And then logic diagram. What is the diagram of that? Here we won't call that as circuit diagram. We will call all the digital circuits as logic diagram. Then we have the truth table. Truth table is for if I give this input, what I'll get in the output. That is truth table. If my input is like this, what I'll get in the output. So for that we can study using the truth table. And switching circuit. So easy understanding of the gate. How I can easily understand my gate, I can study with the help of switching circuit. So for all the gates what we have seen in the previous slide, we will be discussing all these topics: symbols, logic diagram, truth table, and then switching circuit. All these topics we will be discussing. So first we will start with the AND gate. So I have the four things: symbol, logic diagram, truth table, and then switching circuit. I have four things in my hand. First we will start with the symbol. So this is the symbol of my AND gate, and it is having how many inputs? Yes, we have two inputs, and these two inputs are what? These two inputs are binary input, and obviously the output will be a binary output. Yes, correct. So here I represent the same using a logic diagram. So in the place of this symbol, I represented a block here. What this block can do? What function this block can do? The block can do AND function. And what are all its inputs? A and B is its input, and it is giving one output here. So that is what given here. So next we will see the truth table of this. So truth table is I have two different inputs, A and B. Yes, I know digital is having only two things, 0 or else 1. So these two inputs can take any one thing. Either it can be 0 or it can be 1. So only between these two inputs, my inputs will deviate. So here I take both my inputs are 0 and 0. And even in the next case I take, this is still 0, this is 1. And this is still 1, but this is 0. And both are 1, 1. So these are the conditions I take here. And my output here is equal to, see, AND gate will do a logic function, and what function it will do? It will AND. So it will do A dot B. It will do A dot B, A into B. Only if A is also true, B is also true, the output will be true. If both the inputs are true, the output will be true. So which is true? 0 is equal to false. Again, this 0 is also equal to false. So here both the cases are false. So output is false. Here one condition is true, but the other condition is false. So the output is false. So when the AND gate will give me the output, when both the conditions are true, only then the AND gate will give me an output. Why? Because it is y is equal to A and of B. So only in the last condition I have both the cases as true. So my output will be equal to 1 only in the last condition. Any question is there? You can put it in the chat window. See here, the simple example will show this lamp is my output. Lamp is my Y. So when the Y lamp will glow, when both the switch, A switch and B switch, when both the switch are closed, only then the lamp will glow. See here, if I close the A switch alone, till B is broken, B is open, so the lamp will not glow. If I close the B switch alone, till A is open, so the lamp will not glow. Till if I close both the switch, yeah, the circuit is closed now, and then the lamp starts to glow. So this is how you can able to understand the AND gate. So always AND gate is a series of switches. So two switches are there. Only when two switches are closed together at the same time, only then it will get a closed loop, and then the lamp starts to glow, or else it will not glow. see, we discussed like it is all the digital circuits are available in the form of ICs. So the IC where we can see the AND gate is the IC 7408. That is the IC. We have the AND gates. So how many AND gates are present inside the IC? We have totally 4 AND gates are present inside one IC of 114-pin IC. We have totally 4 AND gates are available. So if you purchase one AND gate IC 7408, you can able to make use of 4 gates. The other point are ground and VCC. So for VCC, we will apply plus 5 volts and connect the ground pin to pin number 7. And we know AND gate is having 2 inputs for the first AND gate. For the first AND gate, 1 and 2 is the input and 3 is the output. For second, 4 and 5 is input, 6 is the output. So similarly, as per the pin diagram, you can give the connection and you can operate all the 4 AND gates. So when the output of the AND gate will be 1, when you will get the 1 output? When will you get the 1 output for the AND gate? Yes, whenever there is, when both the switches are 1, both the switches are 1 and 1, the output will be 1 here. Or else for all the conditions, the output will be 0, correct? So next we will go to the OR gate. So you can see the symbol of the OR gate. And what is the output? Y or Z is equal to A or B. A plus B. And come to the logic diagram. In the place of AND, I replaced OR, and it is still having 2 inputs A and B, and it is giving 1 output here. Yes. So here the truth table. So we have 2 inputs here, A and B. So it can be like 0, 0, 0, 1, 1, 0, and then 1, 1. Only the inputs can change in these possible conditions. 0, 0, 0, 1, 1, 0, and then 1, 1. Only the inputs can change in these possible conditions. So how the OR gate will react? OR gate will react like it is OR, this or that. Yes, that is the OR choice. Either I'll take cheese pizza or else I'll take the butter pizza. Anything, this choice or that choice. That is the OR gate. So here the OR gate will react like if any one of my input is 1, then I'll on. For any one input of the OR gate is 1, then the OR gate will on. So here for the first case, only for the first case, both the inputs are 0. So obviously the OR gate cannot able to on anything for you. But in all the things, see here I have 1, so the output is 1. Here I have 1, so the output is 1. And in this case, both the inputs are 1, so obviously the output is 1 here. So for OR gate, only the first input 0, 0. If nothing is on, OR gate cannot able to do anything. It still remains off only. If any one input is on, yes, it will give you the bulb to glow. So here we have like again I have a bulb, but now this time for OR gate I have connected the bulbs like in parallel combination. So if both the switches are open, the circuit is not closed, lamp will not glow. If I switch A, to on state, it goes to the closed condition, so the lamp will glow. If I make only B to on, circuit is closed, lamp will glow. If I make both switches to on, circuit is again closed, the lamp will glow. So only for the first condition, both the switches are off, the lamp will not glow. In all other conditions, the lamp will glow. And this is for the OR gate IC 7432. So this is the number of the each ICs. So here also I have 4 OR gates, and similarly 14 pin is VCC, 7th pin is ground, and then Here 1 and 2 are inputs and 3 is my output. Similarly, you can realize the other gates also. So next comes a very simple gate. It is NOT gate. The NOT gate is having only one input and one output. NOT gate is very famously called as inverter. Whatever it will give, it will invert. If I give 1, it will invert to 0. If I give 0, it will invert to 1. So what you say, if you say yes, that will give you no. If you give no, that will give you yes. That is the work of NOT gate. Okay. So that is represented as C is equal to A bar. A is inverted. If A is 0, output will be 1. If A is 1, output will be 0. Yes, so that is given in the truth table here. If A is 0, output is 1. If A is 1, output is 0. And logic diagram of the NOT gate, one input and as well as one output here. And here, see, the switch is connected parallel to the lamp. So if the switch is open, the circuit is closed here and the lamp will glow. If the switch is closed, the circuit is shorted via the switch A, so the lamp will not glow. So if the switch is open, the lamp will glow. If the switch is closed, the lamp will not glow. So the NOT gate operation is realized by this circuit. You can simply remember with the help of this circuit. So for the NOT gate, I have IC 7404 is there, and the NOT gate inside this IC totally we have six NOT gates are available here because it is having only one input and one output. So in the same space of 14 pin IC, I can able to put 6 NOT gates. So the space is sufficient to place 6 NOT gates because of one input and one output. And similarly, here the VCC is pin number 14 and ground is pin number 7. So then we will move to the NAND gate. NAND gate. So NAND is, we call it as AND plus NOT. NAND we call it as AND plus NOT. Okay, AND we know two inputs is there for AND gate. Output will be A dot B. Okay, if I put a NOT gate in the output, it will become A dot B whole bar. All the outputs of AND gate, if you invert, then that is NAND gate. Okay, so we can just recall what we discussed in the AND gate. So AND gate, when the output will be 1, only when both the inputs are 1 in the last condition, the output is 1 for AND gate. For all other previous condition, the output is 0 for AND gate. If I put a NOT gate, if I ulta all this output, then what I'll get? Only for the last condition, I'll get 0 and all other conditions, I'll get 1. Yes. So here you can see only for the last condition, I received 0. All other conditions, it is 1. Why? Because what is my expression? My expression is A dot B whole bar. I multiplied, I ANDed 2 inputs and whole bar to that. That's why it is 0 only for the last condition and all other condition it is 1. So how to remember the symbol of AND gate? Just draw NAND gate here. Just draw the AND gate. Put one bubble. Put one bubble. Bubble always represent the output of that gate is inverted. Bubble always represent the output of that gate is inverted. AND gate IC we have 7400. 7400 is the NAND gate IC. As we have seen in all the different ICs, here also still we have 4 gates in our IC diagram. 14 and 7 is the same, VCC and ground. Pin number 1, 2 are inputs and 3 is output. So next we will move to the NOR gate. NOR gate is OR plus NOT. OR plus NOT. So draw the OR gate. In the output, put one NOT gate. Then that is what the operation of NOR gate. So here what you will get? Here input is A and B. Output is Y is equal to A plus B. So here if you invert A plus B, output will be Z is equal to A plus B whole bar. A plus B whole bar. So here my inputs are again the same thing, 0 0 0 1 1 0 1 1. My output, we will recall what we discussed in the OR gate. In OR gate, for the first input 0 0, output is 0. Other than that, for all the inputs, the output is 1 1 1. If any one condition is 1, the output of OR gate will be 1. If you put that, if you give that input to the NOT gate, then only for the first condition it will be on. All other conditions it will be 0. Only for the first condition it is on. All other conditions it is 0. So how to easily you can recall the symbol of NOR gate? Draw the OR gate, put one bubble in front. Draw the OR gate, put one bubble in front. So NOR gate IC is 7402. Okay. So here too we have four NOR gates, but you can see all the gates are ulta, inverted. Pin number 1 is output, 2 and 3 is input, 4 is output, 5 and 6 is input. So you have to remember when giving connections to the NOR gate, you have to always refer the pin diagram and do the connections. So then comes to the two gates which are called as special gates in digital, that is XOR gate and then XNOR gate. So we will see the symbol of the XOR gate. We have again 2 inputs and 1 output. And inputs are always common. Just remember the 0 0 0 1 1 0 1 1. And this is the symbol of, see, this is the symbol of XOR. A XOR of B. How the XOR will behave? When any of my input is 1. See, in this case, B is 1. In this case, A is 1. If any of my input is 1, I should give 1 in the output. If any of my input is 1, I should give 1 in the output. If all my inputs are common, same, I should give 0 in the output. If all my inputs are 0 or all my inputs are 1, I should give 0 in the output. If there is a change and if any of my input is 1, then I should give 1 in the output. So that is the logic of XOR gate. It is a special gate. So the expression for XOR, this is called as Boolean expression or logical expression. So y is equal to a b bar plus a bar b. So this in short we can write it as y is equal to a XOR of b. So as short you can write it like that. Again, this is my pin diagram. So it is 7486 IC here. It's similar to the all other previous pin diagrams what we discussed. Yes, only in the NOR it is different. So then it is XNOR. XNOR gate, the symbol and truth table is given. XNOR is just ulta to XOR. XNOR is just ulta to XOR. See, if all my inputs are same, I should give 1. If all my inputs are same, I should give 1. So that is XOR. So this is the symbol of XOR. Put a dot and put a circle over around the dot. That is XOR. So y is equal to AB. Y is my output. Y is equal to AB plus A bar B bar. Or in short, you can write it as y is equal to A XNOR of B. Any doubt, you can put it in the chat window. You can able to follow. See, this is the XNOR pin diagram 74266. See, my gates are facing one each other. Gates are facing each other here. So this pin diagram is also different. So for all the gates except my NOR gate IC and then XNOR gate IC, the pin diagram is similar for all the gates. Only for NOR the pin diagram is different, and only for XNOR pin diagram is different. All other things you can recall the similar set of pin diagrams. So here the gates are facing each other. One side 1 and 2 is input, on the other side 5 and 6 are input. So this is a short review, like which gate is given what number, which gate is associated with which IC. So that is given in short here. So 040007 starts from 74 series. 7400 is given to the NAND gate and 02 is given to the NOR gate because it is a universal gates. So it's a summary of all the gates along with its expression. We can call this expression as Boolean expression or logical expression. So y is equal to A bar. Here AND gate A dot B, OR gate A plus B, NAND gate A dot B whole bar, NOR gate A plus B whole bar, XOR gate go with A XOR of B. XNOR gate go with A XNOR of B. This is a symbol. How you represent the expression. We will also try some of the implementation of this gate functions using a software that is Deeds software. It is a free software. It's very easy for the beginners to start with to understand the logic of the digital thing. And you start from the very basic to the complex level of what is there in your syllabus, like counter, shift registers, flip-flops, everything you can try to understand the logics of all these digital circuits. So the link is given here. I'll put this link in the chat window. So if possible, you can, if you have a laptop, you can just download and see what is that. Then it is the classification of logic families. See, this logic gates, logic digital circuits is coming across two different families. One is like bipolar, and the other one is like unipolar. In unipolar, I have the family of PMOS, P-type MOS, N-type MOS, metal oxide semiconductor, and CMOS, complementary metal oxide semiconductor. So CMOS is very famous one here. And in bipolar, we have saturated and then non-saturated. In saturated, we have like RTL, resistor, transistor, logic. So L stands for logic, emitter coupled logic, integrated injection logic, and here transistor to transistor logic. And in non-saturated, we have Schottky TTL and diode transistor logic DTL. So this is the classification of the uh, simple classification of the logic family. See, the very famous one here is TTL, transistor logic, and the CMOS, complementary metal oxide semiconductor. So these two are there. So we discussed in the very first slide, we discussed like it can understand only two things, one or zero, or yes or no, true or false. So how I can give one as my input, how I can give zero as my input. Yes. So there is no yes or no. We have only voltage, we have current. Only these things I have in my hand. So with these things, how I can make the circuit to understand. So using the voltage, using applying different voltage. So if I tell hi, so it is yes. If I won't react, it means that it is no. So using simple gestures, we can understand the things. So similar to that, so using simple voltage levels, we can understand the digital circuit can understand 1 or 0. Yes, if it is 0 volts, the input is 0. If it is 5 volt, the input is 1. Yes, for simple understanding, we will take if I apply 0 volt to my circuit, that is 0. If I apply 5 volts to my circuit, then that is 1. Yes, I have two things in my hand now. I have two different voltage level. If I apply 0 voltage level, then that is 0. If I apply 5 voltage level, then that is taken as 1. Okay, again we can have the options yes or no, or else true or false. So everything will falls under my yes, my true, my 1, everything will come to 5 volts. My 0, my off, my false, everything will comes to 0. So how I can represent these two voltage level? I have 0 voltage, I have 5 voltage in my hand. How I can represent that using my TTL? TTL is transistor logic. Yes. See, this complete thing is for the input side. This complete thing is for the input. This complete thing is for the output. Whenever your voltage is varying from 0 volt to 0.8 volt, if your input level is between 0 volts to 0.8 volt, then the system will take that as 0. Whenever your voltage is changing from 2 volts to 5 volt, any voltages within this range, then the system will take that as 5 volts. That is 1. 5 volt means it is mapped to 1. Okay. 0 volts to 0.8 volts, it is mapped to 0. Yes. Anything is between this and this, it will take as 0. Anything between this and this, it will take as 1. But any voltage changes in this area, the system, sorry, any voltage between these ranges, the system will not take. Between these ranges, the system will not take. Okay, this is for the input side. Similarly, the gate is giving me the output. It is giving me one output or zero output in different combinations. AND gate, OR gate, NOT gate. So different gates in different time, it is giving me different outputs. So how it is giving 1, how it is giving 0. So whenever the output voltage is between 0 to 0.4 volts, then it will take it as 0. When it is changing from 2.7 to 5 volts, it will take it as 1. Yes, this is for the input side, this is for the output side. If my gate is giving output between these areas, it won't understand. These levels are not used. So only two conditions it can take. When the voltage level is between 2.7 to 5 volt, it will take us 1. When the voltage level is between 0.4 to 0 volts, it will take us 0. This is for the logic level of TTL. If you are having TTL family, then this logic will apply. This is for the logic level of CMOS family. See here my input range is increased. 0 to 1.5 volt is my input. 3.5 to 5 volt is my output. Output level is also varying. My high level is also varying. My low level is also varying. And here 0 to 0.33 is my, if 0 to 0.33, it take as logic 0. If it is 4.4 to 5, it consider as logic 1. Got it? So we have two famous logic family, that is CMOS and TTL. How is the voltage level taken in TTL and how is the voltage level is taken in CMOS? Yes, this is for the simple understanding comparison of TTL and CMOS. So more level is taken as high here. Here equal level of high and equal level of low is taken here. So we will realize the, we will see a simple circuit here. So what we have A input. This is a logic diagram, and in output I have a logical expression, or I can call that as a Boolean expression. So what I have here, I'll see what will be the expression coming out of that.
Priya madam, sorry to interrupt. It's actually 6:10.
Okay, okay.
The participants are actually waiting on another call, so I'll have to end this meeting actually.
Okay, okay. A few more minutes, Parul.
Okay.
Yeah, thank you. So what I have A here, and it is inverted A bar, and here I have B and C. So here it is B dot C because of AND gate, and in the output I'll have A bar plus B dot C. So that will be the output I'll get. So I have an exercise for you. Just you can practice and come for the tomorrow's session. Tomorrow's session is on the same digital. It is a combinational circuits. We'll move to the next session of this one. So you can practice this exercise and join for the tomorrow's session, and it is scheduled at 4 o'clock tomorrow. Any doubts, ma? Any doubts, you can post it in the chat window. Okay. And share the link of that software. You can just download and see what is there in that. Yeah, I have. I'll share to everyone. Just a minute. Yes, I have shared a link on the chat window. You can using that link. You can download the Deeds software. It is digital software for simulating the circuits. We will see one class on that also. How to use that. Okay. Okay, ma. Thanks for joining.